Okay. Yeah, and I see I got the right chairwoman being able to pronounce my terrible last name. Thank you very much. It's a complicated German name. Yeah, so thank you very much for inviting me here. It's really an honor and pleasure. Since I see many unknown faces in the audience, I'm a bit an outsider to this community probably. Because I'm working in the National Metrology Institute of Germany, so I'm a metrologist. I'm building atomic clocks, time and frequency metrology. Nevertheless, I came here to tell you a little bit about our systems that we're building on, our atomic clocks, the Coulomb systems. And I think there maybe we have some overlap and common interest. And I would like to excite you today a bit about the beautiful physics that we do see in these Coulomb systems. It's an experimental talk, so apologize if I maybe do not speak your language in your community. But I try my best, and I will give you first a little overview of what we're doing in Braunschweig, where the National Metrology Institute is situated. Actually, you find us in the Maria Göppert-Meyer building. That's a rather new building. That's our team. I also do have the honor to be guest professor in Osaka University, so there was always a very nice, vivid exchange from our people going to Japan and also many Japanese visitors coming to PTB. It's really nice. In total, we have 5 working groups. So this is just a rough overview of what we're doing. And I told you this is our working host, the multi-ion clock. This is how our motivation came about to deal with many body systems, with complex systems. I will also give you a very short motivation why we do this. And also then precision spectroscopy in the Coulomb systems, really searching for new physics, testing Einstein's general relativity, Einstein's equivalence principle, searching for fifth forces in the nuclei. So many things that are out of the scope of this conference. Here I will focus on the dynamics of the Coulomb system, because our interest arose really when we do precision spectroscopy in these things. Do we really control the dynamics of these bosons? And as Guido said yesterday already in his very nice talk about ions, the bosons are not really quantum yet. Yeah. So if you want to go quantum, better use the spin degree of freedom, because for the bosons you need to be ultimately extremely cold in such systems, and this is a hard experimental way to go. So I will tell you a lot about thermal classical physics today. But I think it's nevertheless very beautiful what kind of textbooks physics we're seeing in these systems, phase transitions and very nice interactions with the modes. And last but not least, we also have a lot of technical things. I will not touch on this at all. We're engineering ion traps, bringing it off to companies, working with industry, testing, benchmarking, calibrating the ion traps for quantum computers, for scalable qubit systems. So there's a lot of technology transfer that we are supervising. Well, let's start again with trapped ions. Guido gave a very nice presentation yesterday, so I don't have to say much. I just would like to excite you about ion clocks, where we believe they're still highly competitive, despite the neutral lattice people doing so well. So it's a head-to-head race. The best clocks still nowadays have a single ion. Yeah, this is the only thing that you can control well with these charged particles that interact very strongly. So you trap them in this incredible deep harmonic oscillator of 10,000 degrees Kelvin. So it's the best approximation of a harmonic oscillator you can imagine. The ions in our ion traps, they even thanks to this deep trap depth, they stay up there for months. So the lifetime of the ions is many, many months. Coherence time can go several seconds, yeah, so even tens of seconds if you like. Then you do not have any systematic shifts, because you really trap the particles at the zero potential, where the electric field is zero. You have a very strong localization, so if you cool them to the quantum mechanical ground state, with a few ions you can do this. With very large ions it's increasingly difficult because of so many phonons. But if you cool it to the ground state, you have a wave function of 10 nanometer only. And that explains why we have this extremely high degree of control, and actually the world record in accuracy is still kept by the ion clocks that are just crossing now this magic border of 10 to minus 18. So this is the aluminum ion clock at NIST. In our system, I will not talk about, we have 2 times 10 to minus 18 right now, but we're pushing it. I hope next year we can report to you the 10 to minus 19 and break this record. But what I really want to talk here about is this high level of control of the pseudospin and the bosonic degree of motion. Guido already showed you yesterday all the phonons. And basically, this is what I'm interested in. So the bosonic degree, because if ions move, they give you time dilation. And time dilation is the killer of the clock. Yeah, this is the biggest, largest systematic uncertainty. We can also do something nice with it because we can test time dilation with quantum mechanical states. We can challenge Einstein and do some very intriguing tests. But at first place, if I want to keep a good control, I really have to control this bosonic degree of motion. Well, to couple really the spin and the bosonic degree of freedom, this is a well-established technique. Dave Wineland got the Nobel Prize for it in 2012. And that's really the basis. This is our tools, our methods, why we can build these very precise clocks with ions. And some people, of course, also use them, as you heard yesterday, to do quantum simulation, quantum computers with the best coherence times. We're all sharing all the same synergies, the same techniques. But for the clocks, it was always a single ion. And when we started our working group at PTB in 2010, we challenged that and we said, can't we now invent experimental methods that allow us to manipulate and measure many-body quantum system and keep the same precision, the same accuracy, and the same control over such a strongly interacting system. So this is how we started, and our motivation there was, of course, to push the instability of the clocks. In a nutshell, if I run this clock and measure time and frequency for 37 days, metrologists need to be extremely patient. Usually we run our clocks for 3 weeks until we get a data point. But then if I scale it up, so a many-body quantum system, I get the same information out in a 1-day averaging time. And that really can boost the boundary and bring you into the 10⁻⁹ regime and beyond. And also do beautiful tests of fundamental physics with it. But you need more qubits in your system. And that's a big challenge in ion quantum metrology. Last but not least, of course, then we can also think of entangled clocks, Heisenberg limit, multi-ensemble clocks. This is what we're working on. But don't worry, this is a different workshop. I will not bore you with this now. If you're interested, I refer to our papers where we really, how we tackle the 10⁻⁹ regime, how we probe time dilation in the Coulomb systems. If you want to see it in a bit fancier way, there was a nice Bloomberg movie done between NIST, PTB, so us at PTB and the Fermilab. So here you see everything about time dilation in the systems and how we challenge Einstein. And there's also a review that we wrote some years ago about how you can use gravitational time dilation shifts to use clocks as quantum sensors for gravity. This is actually also a very strong driving motivation that we will bring our clocks out of the lab, up to mountains, to the field, to really measure time dilation in the gravitational potential and use it as a sensor and complement geodetic measurements. So this was now a lot of motivation that you believe me why we're doing these crazy things with Coulomb crystals. But now I switch gears and I really come back now to phase transitions and non-equilibrium dynamics. So this is the main title of the talk, Dynamics of Coulomb systems. Well, our Coulomb crystals, they can have different dimensions. They can be 3D, 2D, 1D. This is in the hand of the experimentalists. With an experimental control parameter, I can design the system the way I want to have it. In terms of temperature, typically we're not cooling these big crystals to the ground state. Simple Doppler cooling brings you to 0.5 millikelvin, so order of magnitude millikelvin. This is what we're talking about. And you see there's still a couple of bosonic excitations left on the order of 10 or so, so you do have thermal fluctuations. And the way we control these systems, this is our control parameter alpha. That's basically the aspect ratio of the ion trap. Yeah? If I relax this aspect ratio and make it rounder, then I can go from 1D, 2D to 3D. I can choose the phase the ions have. You can also see maybe due to the finite depth of the field of our imaging system, some ions are a bit blurrier, others are more focused. So this is really, you see this 3D helix spiraling up here. And the ions undergo phase transition. The steady state phases are well known, but what was interesting for us was what happens if we do this phase transition, if we're quenching it very fast, very non-adiabatic. And well, what was basically raising the interest was a very beautiful paper by Shmuel Fishman and Giovanna Morici in 2008, where these guys calculated that this phase transition from a linear to a zigzag crystal, from 1D to 2D, which is breaking this rotational symmetry, and bringing up the C2 symmetry. This is actually a second order phase transition. So they calculated the Ginzburg-Landau coefficients for this phase transition, of course on a thermodynamic limit for a very large system, not what we have in the lab, but theoretically it's a perfect pure second order phase transition. And that made it interesting for us because of course that brings in universality. And the question was, can we create defects if we undergo the symmetry breaking in a very fast way, in a very non-adiabatic way, faster than the ions can talk to each other and can communicate? Nobody had seen these defects, and it was always a big debate whether, sorry?
Can I just ask, is the Z direction perpendicular to the plane of the image? Is it just strongly confined? So yes. You're only relaxing it in one direction?
We forced it. We caused some anisotropy so that we really have a purely 2D system. Otherwise, you would actually have like a Goldstone mode because this would be very isotropic and you can rotate. It's really a sombrero head potential. Very good.
You can do as well?
Well, I mean, the problem with ions is every electron that sits on your window breaks the symmetry in this direction. So you could think of bringing it maybe in one of these nice ion traps Hartmut Hefner has in Berkeley, where you have many, many control electrodes to always compensate everything on such a surface ion trap, but it's tedious. I mean, in the beginning, we preferred to have a pure defined two-dimensional system and accept the broken symmetry in this direction, which everyone has. Well, okay, so I lost the storyline. So, okay, we were looking for these defects when we undergo the phase transition in a very fast, non-adiabatic way, because, well, Kibble-Zurek theory tells us that the challenge is how you get over this pole of infinity at the phase transition. Yeah, if you do this very fast, well, Zurek came up with this heuristic theory that there's some freeze-out time where your quench is faster than actually the reaction rate of the system. Where this crosses, the system cannot react anymore, and you just have to calculate basically your correlation length at the freeze-out time and do the classical theory, calculate then the correlation length with respect to the system size, and you get the scaling of the defects with the given Ginzburg-Landau coefficients, which we know thanks to Giovanna and Schmuel-Fischmann. It's a very purely defined system. The laser cooling turns out to be really negligible. It's very highly underdamped, so these coefficients don't really change in our situation. And that was the idea. So we go very quickly from linear to zigzag, and we see what is the defect formation rate. Do we see an onset of scaling? Now, however, I should tell you it's a finite system, and ion traps are typically confined in this harmonic oscillator also in the axial direction. So you have a c to the square scale confinement, and that makes it inhomogeneous. So you do have a higher Coulomb charge density in the center than outside. Yeah, every ion trap shows that. So that modifies the Kibble-Zurek mechanism because the phase transition happens in the center where the charge density is highest, and then a phase front spreads out over the system and runs over the system size. And basically you need to be in a regime where this phase front is faster than the speed of sound if you don't want the ions to communicate with each other. But that reduces basically the system size, and that changes also the scaling of the Kibble-Zurek mechanism. So we collaborated at that time with Wojciech Zurek in Los Alamos and with Adolfo del Campo. And we identified 3 regions in this kind of dirty systems, finite and inhomogeneous, where you undergo the scaling changes from the homogeneous case, I apologize, it's German, homogeneous case, to the inhomogeneous case, and then to an extreme case where you very much sense the boundary conditions of the finite system. Nevertheless, you should see some onset of a power loss scaling, which is expected in the Kibble-Zurek with this Ginzburg-Landau coefficients. And what we did in experiment is we challenged our electronics in the system to do very fast quenches at the microsecond level, faster than the phonons. And then doing a lot of statistic, taking pictures in both domains, also being very careful about nonlinearities in the electronic technical system, that you really know what's the quench rate while you cross the phase transition. And then when we were fast enough, we saw for the first time these beautiful defects. And it's, I know it's awkward to call defects beautiful, but it's really amazing that you can freeze them out and stabilize them. They're very fragile, these topological solitons. So you see like metastable excitations in the scalar systems where ions are trapped on top of each other. This is a very unstable metastable situation. And you see the domain like the zigzag, and zag on the other side, where the domains just don't match and don't fit together. So you have a domain boundary formed. And at the domain wall, you can have like this extended defects where the ions are reordering in such a way. You can have a localized defect. That all depends on our control parameter, so the ratio between radial and axial confinement. Then you have like a localized defect here. And that was the first time that people seen such a thing in a symmetry breaking phase transition in ions. And I just want to tell you here in my simple experimental words why we call this topological solitons. Well, it's basically a field theory in a discrete lattice. So what we do, we map this order parameter. So this is the symmetry breaking phase transition, right? This is the order parameter. Phi can be positive or negative. And the way we calculate this order parameter is that we map A, that's the distance from the ions from the nodal symmetry line. Or here you can see it even more beautiful. A is positive, negative, negative. And the larger it goes away from this nodal line, this is this A parameter. And we map it. Every kth ion is mapped by -1 to the power of k. So even ions become positive, odd ions negative. And then if you do this mapping, you see you have a field which takes on a value positive on one side. And then when you have this kink, it changes very quickly its sign, and then you're sitting on the other minimum. Yeah. So this is this one-dimensional field that you can see there and map there. And this field lives actually on this phi to the 4 model, this Lagrangian phi to the 4 model, which I believe is very well known in this community. And why we call it topological, despite having this very finite system, I mean, it's really protected in the sense that by a local deformation of the field, you can't remove this defect. And if you look at the boundaries of our Coulomb crystal, left and right, you can see and identify if there's a defect present or not. It's really given by the boundary conditions. You would have to move the topological defect completely out of the system to leave and destroy it. So yeah, then we did see an onset of scaling. In experiment, it's always not over many orders of magnitudes because they're small systems. We were fighting to stabilize, but we saw this power law scaling with a given coefficient of 2.7 roughly. Here, this is an experiment, and that's what theory predicted. If you do much, much faster quenches, what we see here, this flattening, that's actually kink and anti-kink annihilation. Because the system is rather small, and if you create many, many solitons and you have kink and anti-kink, they just annihilate and gone they are and they flatten out. So this we could verify with theory and simulations that this is only the region we can trust. And then there were many follow-up papers. In particular, I would highlight the partner et al. If you're interested in the Pallas-Navarro potentials, what mass defects do to the kink system, and also the kink motion. So that was a very nice paper following after that. I really preferred in this paper. And then, yeah, okay, I'm going a bit historical in this talk because yes, please.
In the previous part, is it a finite temperature phase transition in 2 spatial dimensions?
Mm-hmm. Yes. Maybe let me come back. I will talk more about the thermal effects and the thermal fluctuations. Wait until the end of the talk, yes? Let's discuss at the end of the talk, yeah? Okay?
But maybe let me ask the question first. Previously you mentioned the critical corresponding nu is 1/2. Mm-hmm. But if it's finite temperature phase transition in 2D,
the theory is that T equals 0.
Then it should be 1. If it's a finite temperature phase transition in 2D.
Not finite temperature, it's T equals 0. What Shmuel Fishman and Giovanna calculated is T equals 0.
Okay, then for that one, nu is supposed to be 0.63, I think.
0.6.
Yeah, 2 + 1, the Eisen universality class.
Okay, let's talk about this later. I don't believe that the paper is wrong, but maybe it's a different scenario what we're thinking here. Okay, so let me go a bit historically now, how this evolved. So we created now these defects experimentally, stabilized them, but then once in a while you see them leaving the finite system. And that gave us the idea that looking at this is a photo of single atoms that are trapped, ionized atoms trapped in the system, how they're moving and sliding against each other. And that reminds you of nanofriction. That's something that is a very old theory from the 1930s, but in experiment, very little has been observed because you need this high level of control of single atoms sliding over perfect corrugation potentials. So that brought us to this idea, can we study nanofriction now with defects? Well, the well-known Frenkel-Kontrarover model from the 1930s is a simplification that you have a surface, which is basically mapped here by a nonlinear corrugation potential. And then you put a many-body system here, where the particles are connected with spring feathers. And if this distance between these particles, A, is incommensurate with the distance of this corrugation potential, lambda, then you get very interesting effects. And this is what is called superlubricity. That was pretty late discovered, only in the 1980s, so 50 years after the Frenkel-Kontrarover model. There was a phase transition discovered by Perrat and Aubry, which is actually in an infinite system, not symmetry breaking. I will show you in the next slide what it does, but it gives you this superlubrific regime if A and lambda are incommensurate, because the forces acting on the particles can be zeroed basically by the next neighbor forces, or if they're sitting in such a same potential well. And what Aubry saw in '83 is that he doesn't have a symmetry breaking, but an analyticity breaking. That makes it a bit hard to explain, but please have a look. This is what he calls the Hull function. So when you plot here the coordinate of the particles without this perturbing corrugation potential, and here you plot the coordinate of the particle under the presence of the corrugation potential. And if you plot this and you tune up the strength of the corrugation potential, you come into this, from the free sliding to the pinning regime, you see it breaks up. And this is what they call the devil's staircase, because it looks so funny. Yeah, so you get this analyticity breaking of this Hull function, and that's the signature of this phase transition. In an infinite system, no symmetry breaking, only this. And well, theorists then proposed in 2011, why don't you use trapped ions to study this? You could put a cavity around your chain of ions and mimic this corrugation potential. That's a standing optical lattice, so a Stark shift that traps the ions. And then you put the linear chain of ions, and you could basically, maybe you can see this phase transition. So there were many theory proposals. And what are the predictions of this theory? Because in lab, everything is always finite. We don't have thermodynamic limit. So you put a few particles in such a cavity, then you do see some symmetry breaking effect. Symmetry breaking comes in finite systems when you go from free sliding to pin phase. And what you also should see, what is predicted, you should get a vanishing soft mode, where in the pin regime, this phonon takes on a finite frequency. And at the phase transition, it stays at 0. In a very huge system. In a finite system, it actually takes on a little finite energy again. But at the phase transition, it really vanishes. So this is the theoretical prediction or signatures of this Aubry transition. And while we were heading out to this, we didn't know about Vladan Vuletic experiments. So he did parallel to us very beautiful experiments exactly in this scenario, in this setting, a cavity, and then trapped ions in his surface trap. And he published that in 2015-16, so I refer to his papers, very beautiful work on nanofriction. In parallel, we did it in a different way. We are lazy metrologists, and we don't want to have a cavity in our system, because our clock is very allergic against electrons and dielectrics in the nearby neighborhood. So we don't want to touch our system. But we had the idea back then, why don't we introduce a topological defect to get the symmetry breaking and the phase transition? The idea is, if I want to go into an incommensurate regime where the spacing of one chain is different than the spacing of the bottom chain, yeah, I can introduce a topological defect because here I have a completely different periodicity. And what we don't have, it's basically a self-organized system with back action. We don't have a fixed corrugation potential. We don't have a lattice. It's not the classical Frankel-Konturova model with the fixed corrugation potential, but this potential comes from the back action of the Coulomb system itself. And I think that's the beauty in it, because this is also how in reality, I mean, a Frankel-Konturova is a simplification, it's a model. But in reality, you do have atoms that are sliding against each other on surfaces. And the atoms are charged, or you have van der Waals interaction, but the atoms give this corrugation potential. And then the top chain senses basically the potential of the bottom chain. And this is the scenario that we have. So it's self-organized and with back action. And we break the commensurability by introducing a topological defect. And our control parameter to search for this transition, again, is the aspect ratio, radial to axial. So basically, we're moving these two chains closer together or putting them further away. And what did we see in experiment? Well, we changed here this control parameter, moved the ions chains closer and closer, further like this. And then suddenly here at this red line, you see something funny happening. First, it looks very symmetric, very pure. And then you see some symmetry breaking, but you have a realization of different states at the same time. And this is basically, well, maybe I'll show you already here, I go back forth. So what you see here, this is an experimental artifact, because the exposure time on your camera is a few milliseconds, so let's say 10 milliseconds, in order to collect enough light. But during this time, at the phase transition, if you just have the smallest thermal fluctuations, the atoms can, of course, jump from one lattice side to the other, and you see both realizations. And the way we define now this, the order parameter for this phase transition, phi, it's basically, it's the minimal distance between bottom and top chain, and we add up, basically this is a measure for the symmetry in the system. So how do the atoms on the top layer align with the bottom layer? And then you see above the phase transition, it's purely symmetric and zero. And then suddenly it takes on a sharp cusp and you take on a finite value of this order parameter. So with the eye of an experimentalist, we would claim, okay, we saw a signature of the second order phase transition in a finite system, but with thermal fluctuations. And what we're having here, these are these two realizations. So the red and the blue, these are basically these two realizations in the Paris-Navarro regime. When you undergo the phase transition from sliding to pinning, you develop Paris-Navarro barriers. They are, thank you, fixing and locking the system. We also saw the breaking of the Hull function. So exactly how theory predicted, really textbook. And since it's a inhomogeneous system, it starts breaking again from the center and spreading out. And most interesting, we also searched for the soft mode that was predicted by doing basically a laser tickle and searching for resonances of these phonons. And we saw for the first time this localized kink mode that we could set into motion. Now let's see how it looks like. I have to speed up a bit. This is how theory predicted. So the soft mode should go down at the phase transition, take on a zero value, and then come up again. What we see in experiment was very disappointing. Here it fitted perfectly, and here it didn't take on a zero value. Exactly that point we missed. But we have an explanation for it, because if I look now at my Paris-Navarro barriers, and I know I always do have some finite thermal fluctuations. I mean, this thing goes to zero. So even if you have nano Kelvin, pico Kelvin, femto Kelvin, whatever, you always will get a bit of thermal excitation. In ultima ratio, you get quantum fluctuations. So the system will always sense a bit of this nonlinearity at the phase transition. And that actually, these nonlinearities at the phase transition, they can explain that. And we were then driven to study that more. And we thought, wow, how can we explain this phonons at the phase transition? And then we went a step back and we looked at the easier system. We looked again at the linear to zigzag transition, because this is also second order phase transition where you break the symmetry. It's a very similar behavior. The soft mode should go down and come up. So we wanted to see experimentally what the soft mode really does. We did again our laser tickle and studied the soft mode at this phase transition. And together with Giovanni Morici and Hagalanda, we developed a theory that we could then also benchmark with our experiments, and amazingly it worked. So we really could see that the Joanna's new theory with our data matches very well this behavior of the non-vanishing soft mode that is triggered by tiny thermal fluctuations. And what happens, it's actually a nonlinear interaction of this lowest lying phonons with the higher lying high energy phonons. So what we did in the theory is basically we took all the nonlinearities, so these are the phonons, up to the fourth order expanded. Then we wrote the equations of motions of these different phonons, and then you do a time average over the whole phonon bath except the two lowest energy ones that are of our interest. And the argument is because the high layer phonons, they oscillate very fast, so you can average them out and take them out with the time average, and you get basically an effective phonon Coulomb environment that is then changing the behavior of the lowest phonons. And you see then here you get a frequency, eigenfrequency that scales with the temperature. And to summarize this, it's basically the soft mode sees the modified Coulomb environment due to the oscillating phonon environment. Yeah, this is Floquet physics. So you very quickly average out the time oscillations of the high energy phonons. And with this, we could for the first time really describe this crossover under thermal fluctuations at a finite symmetry breaking phase transition. And we could also review this paper where it was claimed that there's a temperature-driven structural phase transition where they saw the criticality shift with temperature, but it's not. It's really a thermal crossover, the regime that we have. So I think that also puts a new light on this work. And now let me just make some advertisement for Lars, who's also here in the audience, and we'll have a nice poster tonight. All this latest work that I don't have time anymore, I will refer you to Lars' poster. We challenged then the quantum regime. Is tunneling possible over 10th of micrometer, where people said no? It's quite funny. I mean, you wouldn't expect that atoms would tunnel over 10 micrometers. Surely they don't. But it's a collective excitation. So we again are interested in this quantum fluctuations at the Aubry phase transition. And what we see is, I mean, it's the collective excitation that has to tunnel. So you can write the wave function of this effective quasi-particle, which mass can be rather flexible. You can tune the mass. It can be very tiny. Lars solved the Hamiltonian for this quasi-particle, and we see beautiful quantum physics. Yeah, maybe here better to see. You get the splitting in the energy spectrum of the plus and minus wave function way beyond the classical energy barrier. So you have here a tunneling regime where the eigenvalues already split up. You see the tunneling of the kink up to a certain temperature, up to 10 microkelvin. So there is indeed quantum fluctuations also driving the wave transition in the phase transition in the quantum regime. And this is the last slide now, also just a teaser for the poster. Since we love topological defects, we also use them then to switch on and off energy transport in the systems from sliding to pin phase. So Lars studied heat transport, energy transport, and all this is on the poster. If you're interested in this heat transport with nonlinearities, polariton dynamics, there it becomes also with a fermionic degree of freedom. Visit us at the poster tonight, and with this I'm done, and thank you for the attention.
Just to clarify, so you're claiming that for this, you see the incommensurate phase without any extra potential was just kind of two chains of atoms interacting with each other, but they each want to order with the same period if it's all identical atoms. Why would they? Can you kind of give an argument for why they would want to?
Topological defect, right? I mean, in principle, in the lowest ground state, the atoms are sorting like this. That gives them the lowest potential energy, and it's perfectly commensurate. You won't see any phase transition that's boring. But what we did is we did this very non-adiabatic quench, yeah, to force the atoms to not talk to each other, and then have something like this. Yeah, and this is a higher energy state. It's a metastable state. and we freeze out this topological defect, and then you see suddenly you have a different spacing here and here, and under this presence you do see then the signature of the Aubry phase transition, and you get into this free sliding regime. And what I actually discovered pretty late, the biologists also know about such things. It's actually a mechanism that has our DNA break up. So if you have some defects, maybe because of radioactive illumination, and you have defects in the DNA, and you have such a offset, such a different commensurable strings, it causes the DNA to break. So quite funny.
Can I ask another one? Any chance you have like 2 species of atoms, like A and B, which would want to which might have this incommensurate phase as the ground state?
Can you speak a bit louder?
You've had 2 species of atoms, like A and
2
B.
species.
Yeah, they might want to have the ground state, incommensurate ground state. Is that possible at all, anyway?
Well, it depends how you realize it. I mean, we did in this partnered oil paper, we also studied mass defects, so different species where we doped the system with a different mass, and that deforms the Pallas-Navarro potential. You get different minima and maxima, so you can trap and localize such defects. But I would say it's a special thing of an ion trap. It really depends how you realize these things. In principle, it's not dependent on the mass because it's just a Coulomb interaction. But in an ion trap, you have a mass-dependent radial confinement. The ponderomotive confinement in this direction is mass-dependent. And then you get some really funny effects, like we could basically trap, by introducing mass defects, we could trap and localize such a topological soliton and also pull it through the crystal with the help of electric field, and then do a lot of funny things. But I would say this is not the original Frankel-Kontorova physics. That's a specialty of the ion trap.
Hi, thanks for the very nice talk. I was wondering, what is the lifetime of these topological defects? Because I assume that a collision in the vacuum would destroy them, right?
So we're not working under cryogenic environment, but it's a room temperature setup. So the lifetime, it depends really how long you didn't open your vacuum chamber. In the beginning, it was terrible, just a few hundred milliseconds. Now it's more like several seconds. It's really the collision rate that you have at 10 to minus 11 millibar. But that's really enough. I mean, we do a lot of statistics. We prepare the system. Now we developed the algorithm that can automatically do particle detection to trigger then the experiment when you do something. But you have a second time to do funny things.
Okay.
Yeah.
Since you're seeing the fluctuations in more or less real time, I guess, huh?
Real time? No.
Well, your single shots at least. So what I'm wondering is if you have access to fluctuation spectrum, or if you can see the amplitude of those fluctuations and extract critical exponents out of this.
No, fluctuations are on a much faster time scale. So this is beyond the... You have to then do many realizations, and but you don't see it in one destructive measurement. Yeah, so it's washed out. So are you interested in the kink fluctuations that is oscillating back and forth, or what fluctuations do you mean?
Well, the fluctuations you showed to us. So when you showed the picture with the close by atoms, where you said within the illumination time of your camera, you saw them appearing at different positions. So this tells me that you have access to this time scale.
Yeah, that's true. Yeah. So when the kink is changing at the Aubry transition between the two different minima, you can see these fluctuations, but I mean, it was like a time average that I showed you because of limited exposure time, but we see the amplitude of these fluctuations. That's what we can tell. But we couldn't do like a non-destructive measurement to really follow. Yeah, this is a different challenge.
Well, but if you know the average amplitude as a function of some other parameter, you can, I guess, have access to this exponents.
Let's talk on a coffee break, but it's, I was thinking about it for a long time because you want to really keep the phase, so you always want to, it's a rather destructive measurement, I would say.
Can I actually return to this question about quantum versus classical?
Yes.
So can you comment on that? Because,
Landau
yes, somehow my understanding was that at least, the previous experiments in this, they all could be explained by a classical, like thermal, thermally activated, things. Yeah. Do you think that you see the kind of evidence that it's not the case?
I don't think we see a quantum phase transition. This is not what we're claiming. This is a, maybe that was a misunderstanding. During the talk, maybe that was. It's not a quantum phase transition. I mean, Giovanna and Paula de Silva, they did theory work on this, and they see a different scaling. But this is an extreme regime. That's what I tried to say in the very beginning. If you work with bosons, I mean, their energies are so low, you have to go to a ridiculous temperature that nobody has seen in the lab so far.
But then I think the critical exponent should be a little bit different, right? Yeah, exactly, yeah. So that's
but doesn't it depend on the symmetries you have in the system? It's a pity that Giovanna is not here now. She would defend her coefficient.
That's why I got confused.
But also Wojciech looked at it. I mean, Wojciech Zurek calculated it. He arrived at the same coefficient. So, yeah, mean field, right? Mean field. No, it's 1D. It's 1D. It's 1D. It's a 1D chain.
Yeah, just a comment and maybe question. So this Ising defect and the difference in displacements between the top and bottom chain is really also coupled to the gapless phonon, which is where the displacements are in phase.
Yes.
So, discussion of critical phenomena, if it's appropriate at all here, in principle needs to couple that difference order parameter to this underlying phonon in plane along the chain phonon.
But the coupling.
So that's if you were an infinite system, it was really like a condensed matter system. That would be an important coupling. That goes to a mode would be important.
I reject the sentence if it's a real condensed matter system, because when I was at the ECRIS, with Natasha Kirova, I saw that the experimentalists in condensed matter, they also have very tiny systems because there's so many homogeneities.
I mean, either you discuss matter of principle or you discuss specific system. So as a matter of principle, once you start talking about exponents and criticality and stuff, then if that's your focus, then, which is not necessarily the case in your experiment, you should be talking about this additional coupling to the phonon. But, in a realistic system, you might not see it or it might not be important. But so that's a comment. And the question is, do you see any effect of sort of this additional phonon, which is the in-phase motion of the top chain and bottom chain?
I mean, in the soft mode, we see this coupling. That's what I showed at the very end. Yeah, that was what was softening out the soft mode. Instead of going steeply down and having the zero, it prevents you from doing so in any circumstance. It's just about how close you look to the. If you look very coarse, everything looks like ideal theory. But even in an ultra-cold system at femtokelvin, or again, you have then quantum fluctuations, you always see this coupling of the phonon to the other baths. So I think it's unavoidable. If you claim you don't have it, that's a pure theory without any fluctuation. And in reality, you either have thermal or quantum fluctuations. So you must consider this coupling, yes.
Okay, thank you. That's what I was wondering about. Thank you.
Okay, so we are pretty exactly at the coffee break time. So let's thank Tanja and actually both speakers again.